So, in the previous example, we looked at the moment of inertia of an L-shaped bar about an axis going through the point O and perpendicular to the plane of the paper. And if you recall what we did, we found the moment of inertia of the lower bar, then we found the moment of inertia of the upper bar through integration, and then we added both to figure out the moment of inertia of the combined system, the lower and upper bar, which is the L-shaped bar about point O. And we used integration. Now know that we don't have to, well, the basic fundamental principle is to use integration, but once we've used integration for one figure, we can, and we figured out the moment of inertia, we can keep that relationship. We can store that relationship and apply it to some other body that has that figure in it. So we'll look at that next. Alright, so for this course, I would expect the Engineering 2202 students to know how to apply the moment of inertia principles using integration and figuring out the moment of inertia, as well as what we're going to do next, which is simply to look up the moment of inertia in a table. So for example, if I have a thin homogeneous plate, uniform thickness, mass m, and we wanted the moment of inertia about the x, y, and the z axis, well, I can go to Appendix B. I can just go straight to Appendix B, and I can look up in Appendix B. You'll see Ix, Iy, and you'll see those are the area moment of inertia, so, or the polar moment of inertias. And what we were asked for is moment of inertia, mass moment of inertia, because we're given mass. So I'm going to apply a relationship we derived earlier, that the mass moment of inertia is the mass divided by the area multiplied by the area moment of inertia. And another name for this was the polar moment of inertia, right? So anyway, we can find out, we can look this up in a table in Appendix B. And if you look in Appendix B, you'll see it written down as 112 BH cubed. 112 BH cubed. So then we simply plug and chug, because we know the area of the triangle is a half base times height here. Simplifying that, we get 16 mh squared. So we can do the same thing for the moment of inertia about the y-axis, or very similar approach, and we get the moment of inertia about the y-axis, and that turns out to be a half mb squared. Now if we wanted the moment of inertia about the z-axis, well, remember earlier we proved that the moment of inertia about two axes that are perpendicular to each other within a plane, the sum of those moments of inertias will give the moment of inertia about the third axis. Sometimes you'll hear that called the perpendicular axis theorem, but we proved that earlier. So if we wanted to find out what the moment of inertia about the z-axis was, we can simply incorporate that perpendicular axis theorem. So here I have iz-axis equals ix-axis plus iy-axis. Now suppose we wanted to do this by integration. Well, we're going to approach it very similar to what we did with the bar. But remember, with the bar, we looked at an elemental strip. It was 1D, so we looked at an elemental strip of length dr. So now I'm going to look at, this is a 2D body, so now I'm going to look at an elemental area of length either dy or dx, and then some other length that we have to consider. So for example, if I wanted the moment of inertia about the x-axis, well, first of all, I'm going to find the polar moment of inertia or mass moment of inertia. and then I can multiply that by m over a, right? So I can say that the polar moment of inertia is given by the integral of y squared dA. Remember, I need that perpendicular distance from the axis. So I'm looking about at the x-axis now. So the perpendicular distance from the x-axis to the strip is y. So I end up with integral of y squared dA, and my strip here, I'm using a strip that has a length of dy, and my other dimension here has to be in terms of the parameters given. So looking at this point here, this point on the line y equal h over bx, this point would have coordinates xy, right? Now this point here, the x coordinate of this point would be b. So clearly the width of my strip could be expressed as the total length here, b, minus the distance to this point, which is x. So b minus x. So I have the integral of b minus x. My dA is b minus x times dy. Okay, so I have y squared times b minus x dy total. My total integral. Now here's a problem. I still have x in this term, and I'm integrating with respect to y. So how do I express x in terms of y? Well, remember this point x here is on this line, and this line is given by what? Y equal h over bx. So I can simply reverse this and make x the subject of the formula to get x in terms of y. So I know x will be equal to what? B times y divided by h, which is what we have here. Now I have this total expression in terms of y only. I can integrate with respect to y. And that's the major step. The major step in integration is to take the strip, is to choose your strip so that you can get the correct moment of inertia. Now this should be j sub x here, so we'll correct that another time. Now if I look over here, what happened? Oh, there we go. So if I look over here, this is the other calculation for the polar moment of inertia about the y-axis. So now I'm going to choose a strip. Remember, this is my perpendicular distance would be a horizontal line, so my strip has to be vertical. Alright, my strip has to be vertical, so that's why I choose my strip to be vertical. So I have the integral of x squared dA as my polar moment of inertia, and I know that, well, the strip would have a length dx, and its height would be given by y. Remember, it's an elemental strip, so I can use this point or this point. They're both y, right? So my area would be what? Y dx, which is what I have here. Agree? Now again, I have x squared y dx, so I have y in the term that I'm trying to integrate with respect to x. So how do I get y as a function of x here? Well, again, look at point y. Or look at the point that y goes to. That point is on the line y equal h over bx. So we know this point that has coordinates xy must satisfy that relationship y equal h over bx. So I can simply substitute for y here, and I get hx over b times x squared, and I do that integration. Alright, and we'll end up with the same terms we have here and here. Now moving on, let's look at how we apply the parallel axis theorem to the same problem we looked at earlier. So two slender bars, each of length L. Well, again, now we can look in a table. Since we know that the tables exist, we still want the moment of inertia about a line going through point O. Okay. Well, I can look in the tables and I'll see that the moment of inertia about the centroid of a thin bar is given by 1/12 ml squared. Now remember the parallel axis theorem. The parallel axis theorem says that we can find the moment of inertia about any other line that's parallel to the axis going through the centroid by incorporating this relationship here. So we have I, the moment of inertia about line L naught, equals to I, the moment of inertia about a line going through the centroid, plus md squared, where m is the mass and d is the distance between the axes. So we can see the distance between the axes is a half L. So I get, for the lower bar only, I get I01 equals 1/12 ml squared, moment of inertia about the centroid, plus the d squared, a half L squared, times m, which gives me 1/3 ml squared. Now, that was for bar 1, because when you looked in the tables in the back, in the appendix, that was just a thin bar, slender bar. Now, we also know the same thing for a slender bar about that axis, the moment of inertia about that axis. That moment of inertia is 1/12 ml squared. Now, this axis L naught is still parallel to this one here. Right? The only thing we need to calculate that we don't know is the distance d between them. And if you look carefully, just applying Pythagoras' theorem, we can see that the d, keeps flipping, the d will be given by the total distance here, L squared, plus this distance here, which would be L over 2 squared, and that would be d squared, d, because we're applying Pythagoras' theorem. So now to find the d, we just take the square root of that summation. Right? Simple Pythagoras theorem. So now I have my d in terms of a known quantity L. Then I apply the parallel axis theorem again. So the moment of inertia of the vertical bar about a line going through point O here, the end, is equal to the moment of inertia about a line going through its axis, which we know is 1/12 ml squared, plus the mass times d squared, where d is the distance between them. And we figured out d squared was what? Using Pythagoras was L squared plus L squared, L over 2 all squared. Right? So that's what we have here. And we get 4/3 ml squared. So my total moment of inertia is just given by the sum of those two.